Have you ever written a program that had to check for something, like with an if statement? What would happen to your program if that check was skipped for some reason? And what if that check happened to be important for authenticating the user? Now, someone might be accessing a resource to which they shouldn't have access, and now there isn't much we can do about it. Suppose while writing a program, we could embed an extra layer of security in case such a critical check were skipped via something like a side channel attack. In this presentation, we'll talk about how we might be able to mount a defense. We'll start with the basic concept of side channel attacks that focus on skipping instructions, sometimes called fault injection attacks. Then we will talk about the different ways people are authenticated. We'll take a quick detour to talk about some hardware defenses before moving on to software defenses. Then we'll talk briefly about compilers, because that can have an effect on how we try to code defensively. Lastly, we'll wrap up with an example program and some ways we might be able to keep improving. Comparisons are prime targets for side channel attacks, and they're everywhere. This code snippet comes from an Ubuntu source file, specifically the PAM Unix section, which checks your password when you try to log in. If you knew the instruction timing, you could enter an arbitrary password, but if you could skip your way through the if statements, you might be able to return PAM success and log into a system. To skip instructions, we rely on some principles from physics. In an introductory circuits class, it's common to assume signals propagate through logic gates instantly. In the real world, this does take time, even though it's seemingly instant from an end-user perspective. The time a signal takes to propagate depends partly on the voltage. We can use a higher voltage to force the signal through more quickly, but this also increases power consumption. In the case of clock cycles, one of the constraints on a faster clock is the time it takes for the signal to propagate at that voltage. If we finish a clock cycle before the gates settle, we can end up in an undefined state. Conceptually, for a power glitching attack, if you want to reduce the input voltage, you can increase the signal propagation time. Done right, when the clock signal turns over, the gates haven't settled, and you can skip some processor instructions. If you were to try a clock glitching attack instead, you would try to increase the clock cycle fast enough to increment the program counter, but without giving enough time for the gates to settle, therefore skipping an instruction. These aren't the only ways to skip instructions, though. You can also use lasers, radiation, temperature, and other environmental factors to disturb a circuit. What might be some consequences of successful instruction skipping attacks? This type of attack typically requires access to the hardware, along with time in a controlled lab environment. So this usually has a very specific target where you can spend the time, money, and expertise figuring out the circuit design and the program sequence. Cryptographic algorithms typically go through multiple rounds of calculations to create ciphertext. The graphic we have here on the right represents a round of AES encryption. The encryption process repeats this loop multiple times to diffuse the secret message. If you can skip some rounds, you'll weaken the ciphertext and make it more vulnerable to analysis, possibly even leaking the key. If you have a system that requires two-factor authentication, like, say, a combination of a smart card and a PIN, if the attacker has your card, they might be able to gain access by entering an arbitrary PIN and skipping the right instruction. You might be able to bypass part of the secure boot process too and load unsigned firmware on a device. Even if that device isn't the target on its own, it could be a subcomponent of a larger system like an aircraft or a ship or an industrial controller, and that compromised device could have a major impact. Here we have a non-exhaustive list of authentication methods and how they might be vulnerable to instruction skipping attacks. Passwords are ubiquitous, but they aren't the only authentication method. We usually treat those as a one-time deal. You set your password, and the system will store a hash of that password instead of the plain text. Then, when you want to log in, you enter your password, it goes to the same hash function. The system then compares the two hashes, and if they're a match, they allow you to log in. This is the type of problem we talked about previously, because if we skip the right instructions, we're authenticated even with an arbitrary password. Tokens are common for things like web services and session management. The user still has to log in with their credentials, but the server creates a token and sends it to the client. The client then sends the token when it requests something from the server, and the server checks to see if the token is valid. These tokens are time-bound, so even if the user manages to skip the initial authentication and receive a token, they'll eventually need to re-authenticate. Most of us are probably familiar with two-factor authentication, where you combine something you know with something you have, and both are required to authenticate. passwordless authentication is becoming more common too, and that might use, say, biometrics or device IDs, specific email links, or something else. And then zero trust is related to all these things, although not on the slide. It's not really an authentication method, but more of a system or a network design. It requires authentication every time you want to access a resource, and that's why it ties into these aforementioned methods. Even though you don't have to enter a password every time you want to open a document or access a website, your token or device ID or something else may be providing authentication after your initial login with your password, or more likely, your two-factor authentication. That ongoing security check helps keep a single breach from becoming catastrophic. Compare that with a traditional perimeter defense system where once you break through the outer security wall, you're free to move laterally through a network. This is a quick aside to say that the software is not the only way to defend against these types of attacks. Here on the left, we've got a snippet from the reference design for an Arduino Uno. By the 5-volt and ground inputs, we have a capacitor attached to the board. This smooths out fluctuations in the power supply and adds resistance to power glitches. The Arduino also has multiple power inputs. The 5-volt V-in and barrel jack are all parallel inputs that add complexity for an attacker. In the middle, we have a machine that's applying a conformal coat to a circuit board. This makes the circuit more robust, but it also functions as an anti-tamper defense. Interfering with a circuit board would require removing part of the conformal coat, the process of which could damage the circuit board. Fault injection attacks that require modifying the circuit could become impractical if it means damaging the board in the process. And then on the right, we have an example from an academic research paper about tamper-responsive meshes, which are another type of anti-tamper device. Aside from providing a protective cover, this can provide an active defense by zeroizing data when it detects tampering. Environmental sensors are another possible addition that could detect extreme temperatures, lasers, or other abnormal operating conditions that might indicate tampering in a lab. Now back to the software side of things. For a side-channel attack like this to work, the attacker needs precise timing information so they can skip the right instruction and pull off their attack. We can combat this by adding some randomness. If the timing of a critical check changes randomly on every run, you wouldn't be able to predict the timing without knowing the random number generator and its seed, which itself might be chosen randomly on each initialization by a true random number generator. If by chance someone does skip an authentication step, we can add a subsequent check while the program is in a critical section. If we didn't catch them the first time around, a subsequent authentication check should catch the user. By that point, they may have already gained some information or done some damage, but we can mitigate the consequences. To prevent false positives, then instead of doing something drastic like crashing the program, we could simply challenge for authentication. An example might be something like how your Canvas session or something might expire and then ask you to log back in. You could collect some contextual information, and this is where things like device IDs normally come in. But with this kind of attack, the device itself is in the attacker's possession, so we would need to think a little differently. Contextual information here might be more like the I am not a robot type of analysis, because launching this type of attack may require lots of reboots and a mechanical operation of the program that doesn't match its normal operating procedure in order to find the instruction order. We could try to duplicate instructions, but this has some special requirements. Compilers try to optimize code, so what you see in your development environment isn't necessarily what's being executed on chip. However, duplicating instructions would make instruction skipping attacks more difficult. Lastly, we need some way to label critical sections. We don't want to rely on developers to code around this kind of problem on their own because the results would be inconsistent. If we have some kind of library or common function, a preprocessor directive, or something else, then it would be much easier to deploy, more readable, and more backwards compatible. As we just started to mention, your compiler has an effect on how we defend against fault injections. Not every stage in the build process will be a factor, but we need to be cognizant of the build process to guard against a false sense of security. The pre-processing step doesn't add any vulnerabilities, but it does provide an opportunity. Pre-processing instructions, pragmas, and so on could be a way to label important sections of code that need to be treated differently in the subsequent steps. This is already common practice for software that has to run on different hardware platforms with different characteristics. At the intermediate representation phase, we're converting to assembly language and our instruction set may look very different from what we wrote. Though harder to read than modern programming languages, we have to watch out for the branches, jumps, and comparisons that are the prime targets for fault injection. The optimization step is what can really undo our efforts if we're not careful. If we added duplicate instructions, for example, the compiler will likely remove them unless we disable optimization, which is itself not desirable. Additional security checks may also be reordered and not happen at the time we expect. Let's move on to a very basic example program. Here we have a simple C++ file that represents a program with some secure section. After initializing the program, we do something to authenticate the user. The authentication status is set as a global atomic variable because multiple threads will need access to this. Then we enter our secure area, where we'll create a new thread that will function like a watchdog timer. That thread will run in the background while our main program operates, and this thread will randomly check our authentication status. The idea here is that our authentication boolean was initialized to false, so if the attacker skipped the authentication instruction, the boolean is still false, and if we check again later, we'll identify the error. Once we're done with our secure section, we detach the thread and let it close. Next, let's take a look at the other thread. The watchdog thread needs to know if we are in a secure area and whether or not we're authenticated, so these are our two atomic booleans. When the thread first starts, we seed our random number generator with the system time and proceed into our periodic checks. First, we identify if we're in a secure area. If we aren't, then we don't need to check anything. Next, we proceed to see if the user is properly authenticated. If not, we take the overly simplistic route and simply crash the program. If the user is authenticated, then we can let the function sleep by some random time on the order of seconds before checking again. If all we did was add repeated credential checks, then a determined attacker might be able to just skip them all. But by adding some randomness, we've made their job more difficult because it would be impractical to determine the precise instruction timing. Instead of digging deeper into code improvements, let's take a step back and combine our ideas with some principles from model-based systems engineering. We won't go through all of these steps. Our focus will be on the use cases to work on our high-level design. We'll start with a very abbreviated concept of operations. These normally span many pages, but we'll keep it very simple. We'll say a user will try to operate a program containing privileged information, and the user will need to provide proof of identity to the program. The program will compare the user's proof with an authoritative copy and grant access if they match. While the user is accessing privileged information, the program will run periodic checks in the background to ensure the user is authenticated and their credentials are current. If the user's credentials are not current or authentic, the program will challenge the user to authenticate themselves. Failure to authenticate will prevent the user from accessing privileged information. Successful authentication will allow continued access. With that ConOps, we try to make something called use cases. Use cases are helpful because they let us determine system interactions and then generate requirements from those. When coming up with a design, this is faster, easier, and less expensive than diving into code straight away, and it will yield a better design in the end, especially for systems where safety is a major factor. To get an overview of our use cases, we can look at the use case set. For brevity, we've skipped some steps to get this far. If you had a more detailed concept of operations, you would try to draft something called a design scope. The design scope is the arbitrary box you draw around your system so you know what you're designing and building. It defines the outer boundaries of your system. For example, you aren't likely designing Azure Active Directory, so you would probably treat that as an external function, but the security watchdog thread is definitely internal to our design. We'll start at the very top of the diagram with the top level use case. So, operate secure system sounds very generic, but you can think of it as the main function of the design. We start here, and this use case will call other lower level use cases as if they were functions. So when we start our system, we may want to authenticate a user, so we call use case 1 authenticate user. Now, the red lines are extensions, which represent an off-nominal condition. So fat fingering your password isn't a big deal, but it's still an authentication failure, so we need a use case to handle that. In extreme cases, we may need to lock out an account or even wipe the system data. At the high level, we want our system to enter and exit secure operation zones as necessary, so we can call those use cases as they come up in the program. We know we want to have a secure watchdog, ensuring that we are authenticated while we're in a secure zone. So when we enter a secure operation zone, we'll also call the secure watchdog. We want to look at some of the details in this presentation, but not all of them. I just want to give you an idea for this model-based systems engineering process without bogging you down in all the details. Let's take a look at the details for our top-level use case. We'll start out with text-based use cases, and once their content settles, you would normally transliterate these into a type of flowchart called an activity diagram that spells out your requirements in an easily traceable way. The goal here is to identify the interactions between different entities in your system. Starting at the top, we've labeled our use case as use case 0, operate secure system. This use case has a precondition that must be satisfied before it can be run. Here we expect our system to be powered on and operating. Then we need a trigger which causes this use case to fire. Here the user begins interacting with the system, maybe moving a mouse or hitting a keyboard or something. The post condition is what should be true after this use case if it succeeded, which is why we say the program should exit successfully. The main success flow is the happy path, the actions that happen when things go smoothly. After our user triggered this use case, we'll start with a user authentication. So in use case 1, this is the step where we call one of the sub-use cases that we saw in the use case set earlier. After being authenticated, we might do some non-secure computation, but that's not something we need to detail here. Of greater interest is when we enter the secure operation zone. We'll do some computations in there and eventually exit it. If everything went well and we're at the end of our program, we can clean up and exit. But what happens if we have more than one secure zone or an error occurs? Well, that's what extensions are for. The number here indicates the step at which this extension could be triggered. So instead of relinquishing our resources at step 4, if we have more secure operations, then we would just proceed to step 2 and we would loop back through the program. Now we can take a look at a sample of the sub-use cases. The use case on the left is for entering the secure operation zone, and it's called by our top-level use case. This in turn calls the security watchdog on the right. Starting with use case 2, our precondition is that the user is already authenticated so we don't expose any data. We are in this use case because we reached a block of sensitive information, and once we're done, we want the secure block of logic to be complete. Our main success flow is that we re-authenticate the user. We are digging into this use case right now, but we don't necessarily mean we're prompting them for a name and password again. It could be a flag or a token or some other metric that we're checking. And then we set a flag to mark that this is a secure section of code. Next, we enable the security watchdog, which is a different use case, so we move from step 3 here over to the use case on the right. Now the security watchdog will check the program flags to see if the user is authenticated. The program will then tell the watchdog the user is authenticated. This is the step where we would catch someone using an instruction skipping attack. Because we're assuming things go well, we can have the watchdog sleep. Our exceptions, or extensions in this case, here include pausing the watchdog in step 1. We may not want to terminate and recreate the watchdog every time we enter a secure zone, so this helps us keep it alive but sleeping. On the other hand, if the program is closing, then we want to have another extension where we terminate it. I chose exception and use case because terminating the watchdog violates the post condition defined in the use case. The last extension is about authentication. If we are not authenticated, then we make an effort to do it. If we are unsuccessful, we kick things back up to the higher level, but if we do get proper authentication, we can proceed normally. Assuming things went well and the watchdog is sleeping, we bounce back to use case 2, where we move on to step 4, where we execute our secure logic. Now, we have an extension here in case we aren't done. If there's still more logic to execute, we return to step 3 and the watchdog runs again. Once we're all done with our secure logic, we exit use case 2 and go back to the higher level. We will look at one last use case to see how we can embed some flexibility into the design. This is how we authenticate the user. The main success flow is written as though we use a typical username and password. The user enters their credentials, and then we compare it with a copy stored in the system and set some sort of flag accordingly. In our extensions, we have the option to use token-based authentication, which could be in place of or in addition to the main credentials, because we can execute both step 1 and extension 1a if necessary. If we fail to authenticate, then we can use a sub-use case to handle the retry. And lastly, if you use multi-factor authentication, typically you validate your credentials first, and then you get a code or some kind of push notification. So that's why I put the extension here in step 4. We didn't go too deep into our theoretical program, but thinking through the use cases helps us identify functions we need to design or other things that we might need in the process. More robust authentication, such as a combination of token or passwordless options, would reduce our reliance on passwords, which is a common problem in security. Trust also doesn't have to be binary. Different types of information can have different sensitivities, so we might be able to calibrate our program to be more strict with some types of information than others. You could be issued a hidden trust score, for example, which is high right after authenticating, but decays with time. Accessing a system from a typical location might be high trust, but an unknown location or abnormal business hours might be low trust. We can't ignore how the compiler affects our programming, even though it might seem like we just hit the magic make command and our program materializes just the way we want. Now, the last 2 bullet points aren't strictly software, but for this type of attack, good hardware design can go a long way because this particular type of attack is dependent upon possession of the hardware. And for continuing this kind of use case work, we would expect to have a more detailed concept of operations, so you can really come up with the interactions for this library. We would want to refine those use cases and then transliterate them into activity diagrams. From there, you would have your requirements and you can start doing your low-level design and implementation. We talked about a bunch of different things today. We learned about the basic ideas behind side-channel attacks that focus on instruction skipping. We learned about different authentication options and how we can fortify our systems via hardware or software design. We talked about how the compiler affects our attempts to secure our programs, and we looked at an example and some ways we can continue improving our system security. Thank you.